Hi, in this video, we will be proving the existence and uniqueness theorem for first order ODEs. In the case where we have already stated that if f and the partial f over partial y is continuous in some closed rectangle, then there exists a smaller interval in which this t lies such that there exists a unique solution for the IVP. So we must think about transforming the differential equation to an integral equation, as we will recognize it to be an easier form to solve. So what do I mean? Well, we suppose that there exists a differential function first that satisfies the initial value problem. Then, because f becomes continuous by assumption, then we can integrate it and obtain the following equation. And we actually showed that the solution to the original IVP is actually the same solution to this integral equation. So this means that if we can solve the integral equation or show that a solution exists for the integral solution, it means that the solution exists for the differential equation as well. So that's the first step of our proof. Next is that we need to understand the other method in solving this integral equation will be known as the method of successive approximation, or also known as Picard's iteration method. And the idea is as follows, is that first we start with an initial function, and the simplest choice will just be equals to the IVP, so it just equals 0. Then it satisfies the initial condition already, although it might not satisfy the differential one, but that's okay. Then we approximate not 1 by substituting this 0 into phi s in the right hand side of equation 3. What do I mean? So because you have here, so you just sub 0 here, the function 0, and we result in getting this new phi 1, which is the integral of 0 to t of f s comma phi naught s ds. And then we obtain phi 2 by now subbing this phi 1 into the f, and then we continue all the way. And this gives us a sequence of functions where every member now satisfies the initial condition. But in general, it might not satisfy the ODE. But if we can find a stage where the phi k plus 1 equals to the phi k, then our phi k becomes a solution to the ODE, the integral equation. And because it's a solution to the integral equation, it becomes a solution to the IVP as well. And then our sequence terminates, because if this holds, then all the back will all be the same already. And so we need to ask some questions for us to prove that this will hold. And the 4 questions to be asked is that whether all the members exist. Why do I ask whether all the members exist? Well, because these are all functions. They're not just numbers anymore. When we integrate this, we become functions, and we want to ensure that the functions are still well defined. So we want to ensure that the sequence still exists, and that what happens is we want that the sequence to converge in the end. And after converging, what will be the properties of this limit function? And in particular, what we want is that it satisfies the integral equation and thus the IVP. And the last question is whether the solution is unique. And actually, this uniqueness is quite simple. So what we want to do is we now look at an example first to relate back to our proof later on, as we'll see the similarities in solving this specific example. So let's just say we got IVP here. Instead of solving it the usual way of variable separable, let us use the basis of Picard's iteration method to try to approximate and think about it. So what we get is we get the following integral equation, and we start with the initial approximation equals to the initial value 0. So what do I mean by Fi1? Well, you see, you got this as your integral solution. So 2s bracket 1 plus phi naught. And what's phi naught? Phi naught is 0. So this is 0. So it's 1 plus 0, which is 1. That's why you get 2s in the end. And when you integrate this, you get t squared. Now, what's phi 2? Well, you get this. Now, but you replace phi with phi 1. So when this is phi 1, that means this is t squared. So that's a s squared, basically. Then you get this t squared plus t4 over 2. And then you sub this t squared plus t4 over 2 over here and keep repeating it. And what you see is that eventually you can prove using mathematical induction that phi n t equals to t squared plus t to the power 4 over 2 factorial plus all the way plus t to the power 2n over n factorial. And what we can see from the plot is how our phi changes over time, whereas you got phi 1, then phi 2, then phi 3, all the way. And it follows that phi n will just become the nth partial sum of this infinite series. Hence, the limit of this phi n will only exist if this series converges. And we can see that this series converges by applying the ratio test. So, what you can now also identify is that the phi will eventually converge to e to the power t squared minus 1. If you remember your power series. But that's not really necessary for our discussion. Just note that we can visualize how the convergence of the sequence more clearly by now plotting what is this phi t minus each approximation. So at the start you get this and then you keep going down. So as the more and more times you approximate, you actually realize that your functions get closer and closer to the same value, because it's like 0 ma. So it gets closer and closer to the same value. So this figure shows that there's an increasing interval in which the successive iteration becomes a good approximation for the solution. And so we already answered the 3 questions. Well, the first one is that we already see that it is just a series of, it is just a power series. So the sequence of functions will always exist. And then after that, we see that it converges because by the ratio test. And the third one is that it will satisfy the IVP in the end. And you can just verify that. So the last part will be just showing that it is unique, and to do so is that, okay, so you got 2 different solutions now, so that means phi cannot equals to psi. Then we just minus off them each other, since we will know that there will be a difference, and this is the following result. And we just take absolute value, which is always the standard trick. We recognize that this now will be just less than the absolute value inside. And we further restrict t to lie in some smaller interval. Then this whole thing will just be reduced to the following inequality. So you might be thinking, why is this so? Well, we just see if your t is like restricted within a over 2, then this 2s here can only be at most to a. So that's why it's like you can pull out the big A now, because you got the absolute value, so you can just pull out the big A as positive. Then after that, you just say that this new integral is u. So the good thing about this is that you know that u0 is 0, satisfy the initial. Ut is always larger than 0 because this is modulus inside. And because it's an integral, when you differentiate it, it will just be the function inside. So it's actually the left hand side. You see how it's now related, why you want to modulus it. And then with that, you can bring over, you get this new inequality. Because this is the differential, and then this AUT. And so you bring this over and you think about it. You look at this, and what does this remind you of? This reminds you of integrating factor formula. So an equation that you use the integrating factor on. So you just times the integrating factor, then you integrate both sides. This inequality stays the same, and we obtain the following result. And this, because the e cannot be less than 0, is always positive, that means the u must be less than 0. But then we already said that the u is larger than 0. So that means the only possible way is for u to be equal to 0, which also implies that because u is just this integral and this is always positive, it must be that the psi equals to the phi, which contradicts the hypothesis that they are different. Hence, the IVP in this case will have a unique solution. And we actually recognize that this way of proving will also be how we extend it to proving a general IVP. So, back to solving and proving our theorem, is that first we ask whether all the sequence exists. And we can do so by actually using the mean value theorem. Because, okay, so how do we use it? So we know f and partial f are continuous along some rectangle. And what we will need to do now is, because f is continuous in some closed interval, closed set, so by the extreme value theorem we know it's bounded. So it's bounded by some m, basically. Then after that, what you want to know is that all of them satisfy the initial condition. And so, because this f function is equal to the differential of the 5k plus 1 term, this means that, so they are equal. What does the differential mean? The differential is the slope of the graph. So the slope of the graph, because this is always bounded by m for all phi's, so the slope of the graph will always be bounded by m as well. So I hope you see that reasoning out. And so the graph contains the point 0, 0. It must lie within the wedge shape here. So you see, let's say you got the phi n, okay? What you need is that you know that maximally it cannot exceed m, the gradient. So that means it must stop within this minus b and b, or yeah, so it's like that, depending on how big the m is. So as long as you stay within this shaded region, you'll always able to find the next succession. So that's how we want to do it. So as long as R remains in this wedge-shaped region, then it will always be also within the rectangle, in which case all our members will exist. And if you just so happens that the b over m is larger than a, then you just stick it with the normal rectangle and you'll be fine. But yeah, so what you want is that you already have the original rectangle over here. Then you realize that the gradient cannot exceed this line. You see, so what does it mean to exceed? It means you cannot have this. this is outside the shaded region, so you need it to be staying within this range. So as long as you cut your interval within it, you'll always be able to find the next succession. And this gives us all the sequences, and that's why we want to show that it's only within some smaller interval most of the time, unless this holds. So I hope you understand why all the sequence, the members exist in the sequence. And do they converge? Well, we can use this identity where we just plus the first term plus second term minus first term, so this part cancel out and then you just keep cancelling, okay? So when you write it in this form, you actually see there is the nth partial sum of dot 1 plus this. And so actually the convergence of this sequence is just to show that this series exists. And to show that this series exists, we just need to estimate the magnitude of this function inside. And this can be done by the following method. So we just take the modulus, and because it's an integral, you can combine the integral into 1. Okay, so this is the phi n and this is the n minus 1. Then by the triangle inequality, you just push in the modulus inside. So you get this, and then you look at this and you just use the mean value theorem to pull out the partial f partial y, and then this part you just leave it. You only get the s terms left. So because you know partial f partial y is going to be bounded, so it becomes an m2. And then you think about it, t is within h is minus h to h, so it's also bounded within h. Then you just need to choose some maximum height so that this area is still less than this whole part. And as a result, we see that the max of this must be less than half the max of phi n minus 1. Why? Because you just need to choose a h small enough, such as 1 over 2 m2 or something, and you get this maximum being less than or equals to half of this max. And why you want to choose that h is because then you can, why you want half and not 1 is because you want some fraction, so that when you do this successfully enough, then it will be half to the power n, and this fraction will go to 0. Hence this sequence will converge. And what more is that this sequence converge uniformly in the closed interval. And this will actually allow us to show that the sequence converges to a limit. And so the third step of the proof now is that now, because we know that the uniform convergence, we see that the limit and the integral sign can be switched around. So you can just push in the limit and the integral, and because the function is continuous, you can push the limit in all the way, and you actually get the required solution that you want. And so this actually completes the proof of the existence already. And for uniqueness is what we have already went through. And to show that it's unique, you just do it the same way as your as the example earlier, where you form this becomes the ut, and then this is the differential, and then you show that it must equal to each other, which is a contradiction. So actually this completes the proof, because this is the uniqueness part, and this part shows the existence. And that's it for the proof. And you have actually shown that for an IVP where the hypotheses are satisfied, you'll always have a unique solution. So I hope from this video you've now understood why for ODEs we can just whack some formulas and try to solve it, because we actually know that the IVP will have a solution. instead of blindly solving it. So I've come to the end of this video. I hope you have enjoyed it. In the next video, we'll be moving on to second order differential equations already. And yeah, I'll see you again. Bye.